Have you ever just stopped and thought about how incredibly fast the world around you is actually moving? I mean, picture the visceral, intense energy of police lights cutting through the dark. Up in the air, the light from those sirens is traveling at a blistering speed of 300,000 kilometers per second. It's almost unimaginable. But here is where it gets really fascinating. The exact moment that very same light hits a solid glass slab, it slows down drastically, dropping to about 197,000 kilometers per second. So, that brings us to a pretty crucial question. Why exactly does light just slam on the brakes when it hits glass? It's one of those things that really challenges our basic, everyday understanding of how the physical world operates. You see, it's not about the glass being physically heavier or anything like that. It's actually about something called optical density. Keep that specific concept in your back pocket, because it's absolutely going to be the main key to unlocking the physical behavior of light for us today.
All right, let's dive right into this. Welcome to our explainer on the journey of light, bouncing and bending. Today, we are going to decode some of the most incredible mysteries of optics, pulling straight from our source material. We'll be looking at everything, from how mirrors play tricks on our eyes to how lenses manipulate the very fabric of the images we see. It's going to be an amazing journey, and I am absolutely thrilled to be your guide through it all.
Now look, if you're feeling even a little bit overwhelmed by the physics of it all, seriously, don't worry. As our source material so brilliantly puts it, tenth faux dengue, which basically translates to, we are going to completely crush this. The Josh meter, our enthusiasm meter, is running high today. We're going to crack these complex physics puzzles together, step by step, with total confidence. No stress, just some really fascinating discoveries.
So here is our game plan for today's explainer. First, we'll cover bouncing light and mirror mysteries. Second, bending light and lens logic. Third, we'll tackle the math of optics. And finally, light in the real world.
Let's kick things off with Section 1, Bouncing Light, Mirror Mysteries.
Take a look at the contrast we've got here. On the left side, light hits a concave mirror and just bounces right off. That is reflection in action. But on the right, light hits a convex lens and pushes right on through to the other side. That is refraction. By the end of this, we're mastering both, but let's just stick with that bouncing mirror for a quick minute.
Okay, it's time for a little myth-busting, straight from a really clever assertion reason set up in our source text. True or false? The center of curvature is not a part of the mirror. It sounds like a total trick question, doesn't it?
Well, this brilliantly illustrates the reality of how spherical mirrors actually work. The assertion is totally true, and the reason clears it all up. The center of curvature lies completely outside the reflecting surface itself. Think of it like this. A spherical mirror is really just a tiny slice of a giant sphere, and that center point is merely the geometric center of that imaginary theoretical sphere. It isn't a physical piece of the glass that you could actually reach out and touch.
Now, here is another massive point of confusion for a lot of people that we definitely need to clear up right now. Can a concave mirror ever form an upright image? Because, concave mirrors are basically famous for creating images that are real and flipped completely upside down. It's practically the golden rule of optics, but is it an absolute rule?
Well, actually, there is exactly one magical exception. According to our source material, when you place an object intimately close to a concave mirror, specifically right between its pole and its focus, the mirror completely flips the script on you. Instead of a real, inverted image, it suddenly forms a virtual, erect, and highly enlarged image. It is literally the ultimate physics plot twist.
Moving right along to Section 2, Bending Light, Lens Logic.
I want you to think of a light ray moving through different mediums, sort of like a runner sprinting down a fast track who suddenly hits a deep patch of thick mud. As light moves at an angle from a rarer medium, like just plain air, into a denser medium, like a block of glass, it physically slows down. And because it slows down, it actually bends toward the normal line.
You guys, this is the absolute core rule of refraction. Going from rarer to denser, the light slows down and bends toward the normal. But going from denser to rarer, like emerging from that glass back out into the open air, it speeds right back up and bends away from the normal. And remember that concept we talked about earlier? We are talking about optical density here, not physical weight. That density is what dictates the speed and the bend of every single light ray.
Okay, let's get into Section 3, the math of optics.
Don't let the numbers scare you. Think of this as your ultimate magnification cheat sheet. Let's decode it together.
If you see a negative sign, like that -3 or -1/5, that instantly tells you the image is real and inverted, meaning it's upside down. A positive sign, like the +3, guarantees a virtual and upright or erect image. The number itself, that just tells you the size. A 3 means it's magnified 3 times. A 1/5 means it's diminished, literally shrunk down to a fifth of its original size. Once you know this secret code, you can basically read any optics problem instantly.
Let's test this out with another piece of the math code directly from our source text. -2.5 diopters. Now, diopters are simply how we measure lens power. But if I were to hand you a lens right now and say, hey, its power is -2.5, what does that actually reveal about the piece of glass you're holding?
This is where the math brilliantly does all the heavy lifting for us. Let's walk through the exact calculation. Step 1, power equals 1 over the focal length in meters. Step 2, we just plug in our -2.5. Step 3, we calculate the focal length, which comes out to -0.4 meters or -40 centimeters. And step 4, the grand finale here. That negative sign mathematically guarantees you are dealing with a concave diverging lens. The math literally tells you the physical shape of the glass. How cool is that?
And finally, Section 4, Light in the Real World. Take a look at this. This is Mrs. Iyer's slide projector, taken straight from an amazing case study in our source text. It is such a brilliant everyday application of a convex lens. Mrs. Iyer uses this exact setup to show her students tiny insects, and the lens produces a massive 500 times enlarged image on a screen that is sitting a full 10 meters away across the room.
So how does this actually work? Let's break down the projector's mechanics, because it solves a fantastic practical mystery. Notice that the slides must be inserted upside down. Why on earth would she do that? Well, because to project an image onto a physical wall, you need a real image. And as we just learned from our math cheat code, real images formed by convex lenses are naturally inverted. So, to ensure her students see a right-side-up, erect image of the bug on the wall, Mrs. Iyer has to feed the slide into the projector completely upside down. It is literally applied physics in action.
Okay, let's pivot to something you probably use every single day: traffic safety. Here's one final practical puzzle for you. Why do drivers rely on convex mirrors for rear-view safety? I mean, why not just use a simple flat plane mirror like the one you have in your bathroom?
The answer to that is all about geometry and keeping you safe on the road. A plane mirror just gives you a basic 1-to-1 reflection. But a convex mirror with a magnification of, say, +0.25 shrinks the image down. That positive sign means it's always virtual and erect, so the cars behind you never look upside down. But by shrinking or diminishing those objects, the convex mirror brilliantly expands your field of view, allowing you to see multiple lanes of traffic all in one tiny piece of glass.
Before we wrap everything up today, I want to look back at this really foundational quote from our source material. The ability of a medium to refract light is expressed in terms of its optical density. It is not the same as mass density. This is just your friendly reminder that light plays by its own unique, beautiful physical rules. A material might feel incredibly light in your hand, but to a zooming beam of light, it could be a massively dense optical obstacle course.
And that brings us to the end of today's explainer. I want to leave you with this final, somewhat provocative thought. If light bends and bounces just to show us the everyday world, what else is hiding in plain sight, just waiting for the right lens to reveal it? I challenge you to look at the world around you today, not just as a bunch of static objects, but as this continuous, fascinating dance of light and physics. Thanks so much for joining me on this incredible journey. Keep questioning, keep learning, and I will catch you on the next explainer.